Okay, now we're going to start part 3, where we take a look at 2 ideal wires and 1 real piano wire. First example is a plucked flexible string. The string is completely flexible and does not have any elastic properties. We're going to pluck it at about 1/9 of its length. It's got a length here of 51.51 meters. Okay. We released it. We get a traveling wave. And the simulation showed about almost 2.27 milliseconds, which suggests that the natural frequency of this wire or string is 440 hertz. Notice there were no standing waves. However, if we pluck it in the center, it'll look like there's a standing wave. Okay, there's one cycle. Now let's move on to a more realistic situation where we compare that flexible string with a stiff string or a stiff wire. The stiff wire will have flexibility under tension, but it will also respond. It'll have a characteristic of elasticity, which means it wants to return to its non-disturbed condition. We're going to strike it with a hammer. We're going to start out with, well, first of all, the wire is 1 meter long, and it's designed to have a fundamental frequency of 200 hertz, which corresponds to a natural period of 5 milliseconds. Okay, here's our graph. We're going to plot the applied force via the hammer on this axis. You see, this is a compressed vision up here because here's the center point. 0.1 meters is where we're going to strike the wire. Here's a picture of the whole wire of 1 meter long, and right here's where we're going to strike it. And on this bottom graph, we're going to watch the flexible string and the stiff string. Okay, the hammer force has been applied, and we're about 0.199, about 0.2 milliseconds into the simulation. Down here you can see the hammer force also, and down here below that is the green and the blue trace for the flexible and the stiff string. And here's a close-up. Here's the applied force, of course going off scale because we've got a compressed view, expanded viewpoint. Here is the flexible string response. You see it starts off with 0 slope and comes up and turns a sharp corner. The stiff string or stiff wire does not come up and turn as sharp a corner because it's got this elasticity characteristic and because it's stiff. Okay, we'll continue the simulation and continue applying the hammer force. You can see down here the strings are responding. And I'll take another close-up. Again, the flexible string is responding. You can see its center is a little bit moving to the right of the center of the applied force because we're starting to get a traveling wave going. The stiff string is not responding as flexibly as the flexible string. Now we're continuing the simulations. Hammer force is going to max out here. And now the hammer force is dropping off. The two strings are both still responding. A traveling wave is being set up. Okay, the hammer has been retracted completely, and now we're going to watch these two wires move, but on one graph. We get the reflection at the right-hand side, inversion. Reflection and inversion. Okay, so we've done about 6.2 milliseconds of simulation. the stiff wire is leading the flexible wire. You can see it also has developed some undulations that the flexible wire does not have. Okay, now let's take a look at the force that the stiff wire exerts on the right-hand side where the bridge is located. First we'll look at the time domain, then the line spectrum, and then the autocorrelation and the sounds. Here's the time domain of the force on the bridge on the right-hand side. See, nothing happens until about 2.5 milliseconds, which is half of the natural period. Then the wave gets across to the right-hand side, and we see the force and the inversion. Then about 5 milliseconds later, it gets back. The traveling wave comes back to the right-hand side, and this pattern continues. Here's the line spectrum of the force on the bridge. We see a peak here at 200 hertz, which is the natural frequency of the string. Harmonics, partials. Notice that we have a minimum here at the 10th partial, because we struck the string at 1/10 of its length. Also notice that the peaks of the partials are starting to slip away from the location of the harmonics. The higher in frequency we go, the more the displacement is. Here's the autocorrelation. It's got a peak at 4.823 milliseconds, which corresponds to 207.3 hertz. So the autocorrelation tells us that the pitch is a little bit sharp of the expected natural frequency of the stiff wire. That was the sound of the stiff wire, and here's going to be the sound of a pure 200 hertz sine wave. Okay, that little hiccup there and the sound was me touching the laptop surface, which damped out some of these resonances in the body of the laptop. Okay, is this how a piano wire behaves? Strictly speaking, no it isn't, but it's similar in the sense that the stiff string is going to have peaks at frequencies that are higher than the harmonics, which will lead to this idea of octave stretching or inharmonicity that we'll talk about a little bit. And it does consist of a pulse or a traveling wave moving back and forth across the string, and there are no standing waves per se. Now let's take a look at a real piano string, Bösendorfer C1. First the time domain picture. Okay, there we get a picture of the wave. It's taking about 14 seconds to die away. Here's the amplitude versus the time. There's the sound, part of it anyway. Now let's take a look at the leading part of the wave. In other words, here's the wave I just showed on the previous graph, and we're going to take a look up right in here. And here's the graph of that area. And you can see there's a leading portion that you can't see on this scale up here. But there's a leading portion of about 19 milliseconds, which is a longitudinal wave. It's the vibration in the flexible wire along the axis of the wire, as compared to these waves over these peaks over here, which are longitudinal and transverse, where the transverse vibrations are perpendicular to the axis of the string. So we've got two things going on here. The longitudinal wave is a higher frequency wave. It moves more quickly across the string than does the transverse wave. Now we're going to take a look at the spectrum of the whole wave and see where those different components show up. Okay, here's a spectrum of the C1 wave from 0 to 1000 hertz. I'm using dB when I'm plotting the signal power. Here's our fundamental near 32.7 hertz. Here's the second partial. The strongest partial occurs at 194. It's the sixth partial. And things look fairly regular down in this area, this frequency range. However, when we get over here to the higher range, around 800, 900 hertz, I've circled the transverse peaks, little red circles, and they're continuing on with a spacing of about 33 hertz, which would correspond down here to the fundamental. But you see these extra peaks show up, the ones I show with blue circles, and these are and they're higher frequency, of course. In other words, they don't occur until around 800 hertz, and they are the peaks from the longitudinal vibrations. And then down here is a closer look at this range from 700 to 1000. You see, here's the peaks from the transverse, the red circles, transverse vibrations. And then here are these peaks in blue from the longitudinal vibrations. Now we also note that the peak at the first partial is quite a bit weaker than the strongest peak, and we'll talk about that later on. So this page comments about the different speeds. The transverse wave moves across about 343 meters per second, whereas the longitudinal waves move around almost 5,000 meters per second. Let's take a look at the autocorrelation of that note. This is interesting, at least to me. Here, of course, we have total autocorrelation at zero lag. And here, there's a peak at a lag time of 30.6 milliseconds, which corresponds to 32.7 hertz. So, at least according to the autocorrelation, the pitch of this tone is 32.7 hertz. However, when we take a look at the fine grid line spectrum near the first partial, we see that this is an expansion here of the regular line spectrum, and the peak actually occurs at 32.4 hertz, according to this thing, because this has less resolution. Over here is a fine grid spectrum located right around the first partial. This line here is 32.7 hertz. And you can see the actual peak is flat of the fundamental, or the first harmonic, by about 16 cents. This flatness at the low end of the compass on a piano is something we'll talk about later, as it's an example that's supported by the Railsback curves. However, this example shows that the line spectrum gives the location of the strengths at the various frequencies for a wave, whereas the autocorrelation takes into account all of these strengths and shows where the actual pitch might be located, what frequency the pitch has.